All right, so it is 2 o'clock. We'll go ahead and formally begin. I'm joined by another professor, Alec Drachman here, who's going to be helping to facilitate questions. He doesn't have a webcam, so unfortunately you can only see me, I guess. But so he's going to be monitoring this Q&A and the chat and everything. So if you have questions or things and they're relatively short, you can type them out in the Q&A, or you can raise your hand and just kind of every once in a while, we'll pause and kind of see what kind of questions there are, and we can even call on you, and then you can use your microphone to ask questions that way as well. Yeah, I think that's more or less it. So yeah, you should see at the bottom of the screen, there's kind of the raise hand feature, the Q&A. And the Q&A is good because, right, I think that everyone can see the questions asked there, I believe anyway. And then so when we respond, maybe you have a common question so everyone can hear or see the response to this. Okay, so I guess usually how I like to start classes are with a few administrative announcements. And so I think that would be also appropriate here. So I'm on our D2L page, and we have this just, pretty convenient box here at the very beginning as far as what you should be working on. And so, yeah, you should be finishing up 11.11. That's what we're going to be working on here in today's class. Lab 6, right, that's Tuesday. Well, the pre-lab's already open. I got the email and everything, so that's open, accepting answers. And again, you have until Tuesday night in order to do that. And then, oops, I did a weird highlight apparently with my hyperlink, but if you click on this, right, it goes through all of the detailed information as far as when things are due, the MATLAB code, all that sort of stuff. So it's kind of conveniently placed right there. And then I guess the last thing, I don't remember if it's on here or not, but right, we also have the quiz on Friday. Yes, quiz on Friday. So that's kind of the other thing that you should be thinking about. The quiz will cover 11.10 and 11.11. And so, yeah, those are the kind of the big ones, all of this Maclaurin and Taylor series and its uses, right? So 11.10 is really about how do you find Maclaurin or Taylor series, and 11.11 kind of goes into some of the uses, which are, those limits, integrals, and, actually finding what some non-geometric series converge to. Okay, I think that's all of the administrative stuff. I see that there's one Q&A. I'll just hit answer live. It's S. Are you going to be teaching Math 234 in the future? And I don't know. None of us really know our teaching schedule until middle of the summer or so. They try to organize everything. So that's still a bit out. And here's maybe one more, and then we'll get into the lesson for today. I guess, right. I have here pulled up. So if you would like to start copying down the questions or things like this, you can do that. But this is also available for download on D2L if you happen to find this and print it ahead of time. But we have any form of quiz review sheet or maybe an old quiz. I'll try to post an old quiz at very least. And if I get around to it, I'll try to do a review sheet as well, or maybe one of the instructors has one handy. But yeah, at very least, we can post an old quiz on Piazza. Happy to do that. Okay, well, with that, let's go ahead and start the new math for today. And just want to double check. Good, I am recording. Like I said, I promised some, the other students, anyone who couldn't make it here, that we would have this video available for them. Okay, so I'd like to start with the binomial formula or binomial theorem, right? Because this got a little bit of attention in 11.11. But it's maybe one of the more complicated ones. And so this is all thanks to Newton. Newton really enjoyed this binomial theorem. If you happen to watch my class for 11.11, the first class video, right, I have a quote from Newton saying that he's really enjoyed expanding these things out. And so let's go through this first example, find the first four terms of the binomial series for this function here. So it's already telling you that it wants you to use the binomial series, which is really nice, right? It doesn't maybe have to be this nice, but it's leading to use this binomial series because otherwise you may look at this and say, hey, I know what the power series expansion is for 1 over 1 minus x. And right, so this is just summing up these x to the n's from n equals 0 to infinity. And so you'd say, well, maybe I can just apply a square root to this on both sides, and now I'll have the power series expansion for the square root of 1 over 1 minus x. And sadly, this does not work. And the reason why is because remember, power series, and that includes Maclaurin series and Taylor series and all this sort of stuff, are supposed to be infinite polynomials, right? And so this right here is not going to be an infinite polynomial, sadly. These square roots kind of ruin that. And so it's not actually a power series once you start introducing these square roots and things. And so that's kind of one way to view this. Also, I mean, there's no good way to distribute the square root across terms. So there's a few things that are really kind of off about this. So it's nice though, it says we're gonna use the binomial series, right? And it wants to know just what are the first 4 terms for this. So the first thing we need to do is maybe review what is the binomial formula. And so I'm gonna write it down with a u here. So it says 1 plus u raised to some power k. And so basically what is the power series for this? And it goes that we sum up from n equals 0 to infinity. And we do have these u to the n's here. But then we have these things called the binomial coefficients. So the binomial coefficients go in front here. And these kind of, you know, they have almost parentheses going around them sort of deal. But it's really this choose notation. So it's k choose n. So this right here, using the binomial coefficients, this is the formula for binomial series. And so we want to try to make our function look like one of these 1 plus u to the k's, right? And so let's go ahead and work on this thing a little bit. I have the square root of 1 over 1 minus x. And okay, first thing maybe I could do is say that I could distribute the square root to the top and the bottom. So the square root of 1 is just 1, and the square root of 1 minus x, well, you can't really simplify it at all. You just can, you know, leave it as the square root of 1 minus x. Now, right, we could go ahead and, right, division is the same thing as raised to the negative 1 power, negative first power, and the square root is the same thing as the 1/2 power. So that all together, we can write this as 1 minus x raised to the negative 1/2 power. And so now we can see that we're getting pretty close to what we have up above here. We can just say that u would be equal to negative x. That would be a good choice for u. And it looks like our k value should be equal to negative 1/2. So we've rewritten our function in order to make it look like this binomial series, which we're tasked with using. And we'd like to come up with the first 4 terms of this. So according to this binomial series formula, this should be the sum from n equals 0 to infinity of, and instead of k here, I'm going to have negative 1/2. And then our n variable is still changing, right? First we'll plug in n equals 0, then n equals 1, then n equals 2, so on and so forth. And now we have x, well, sorry, u to the n. U is the same thing as negative x raised to the nth power. Okay, so with that, we've done the bulk of the work. We just need the first 4 terms. So I'm going to start plugging in n equals 0, n equals 1, n equals 2, so on and so forth, and we need to simplify down a little bit. So let's go ahead and start plugging in different terms. So the first off, if I plug in n equals 0, I'm going to get negative 1/2 choose 0 times negative x to the 0th power. Well, anything to the 0th power, right? This is just going to be times 1. So I'm just going to erase that. So that's when I plug in n equals 0. If I plug in n equals 1, I'm going to have negative 1/2 choose 1 times negative x to the first power. Then next up, I'm going to have negative 1/2 choose 2 times negative x to the second power. And finally, I'll have negative 1/2 choose 3 times negative x. We got my negative sign. Negative x cubed. And of course, this would go on forever, but we're only asking for the first 4 terms. And so I brought this up in a previous video as well, but this is a small point of confusion sometimes that comes up that it's worth stating again here, right? So the terms are what's getting added together with, you know, either addition or subtraction's fine as well. So this is the first 4 terms. But if it said find, you know, maybe the 4th degree Taylor polynomial, right, then you would want to make sure that you're going to have an x to the 4th, right? So in this case, because we have 4 terms or 4 non-zero terms here, this is all that we need. But if it said something slightly different, right, then we'd have to go maybe to the 4th degree polynomial, for instance. All right, and so the last thing I want to do probably is try to simplify this, right? So let's recall what all of these binomial coefficients are, and then we'll pause and take a second for questions, I believe. So first of all, you may remember from the pre-class video on 11.11 that anything choose 0 is always 1. And there are kind of some different ways that you can formulate this in order to see that this makes logical sense. It's kind of an extension of these definitions for choose, but a good way to remember this is just anything choose 0 is always 1. And it kind of goes along with this 0 factorial being 1, just as kind of an FYI. Likewise, if you have anything choose 1, it's always just itself. So in this case, we're going to have -1/2 times -x. So if you'd like to, you can combine these and write, and we're going to have plus half of an x. So that's that there. And now here's where you kind of really see the definition. Once you have choose 2 or choose 3 or things like this, you really get to see what's going on here. So what's going on is that you always take this top piece, so in this case, -1/2, and you multiply together so many values. In this case, you're going to multiply 2 values, and each value you're going to drop by 1. So we're going to start off with -1/2, and then we're going to drop by 1. So if we drop by 1, we're going to have -3/2. So those are 2 values being multiplied together. So that's where we stop, because again, we were choosing 2. And then we divide by 2 factorial. So whatever that bottom number is, that's the factorial that you have there. And then we're going to have -x squared. And so let's go ahead and try one more of these just to make sure that we really got it down. We're going to choose 3 now. So again, we're starting off with that top value, -1/2, dropping by 1, -3/2, and then you drop by 1 again, -5/2. So you drop by 1 every single time, and then we're going to divide by 3 factorial, because again, that's this bottom number here. And then we're going to have -x raised to the 3rd power, and sadly, I'm at the edge of my paper here. One more line of simplifying, 1 plus 1/2 x. And let's see, when we multiply all of these coefficients together, let's see, we're going to have a 3 on top, and we have 1, 2, 3 2's all in the denominator here. So this is going to be 3/8, and -x squared is going to be the same thing as just +x squared. And then let's do one more here. In the numerator, we'd have -1 times -3 times -5. So that's going to be -15. And in the denominator here, we have a bunch of 2's, and we have 3 factorial. So we have 8, and 3 factorial is the same thing as 6. So 8 times 6 is going to be, what, 48? And then we have -x cubed. So -x times -x times -x, that's going to be, well, -x cubed. So a negative is going to be positive. Again, this would go on forever, but we were only tasked with finding the first 4 terms, or the first 4 coefficients for this binomial series here. Okay, so I'm sure there are a few questions and everything. I think this is a good place to pause for a second. What are you seeing out there, Alec?
Most recent question here is, on quizzes, exams, should we be simplifying as much as we can, or should we leave the answers with factorials or fractions? So we will have some questions that will be multiple choice. Mm-hmm. So you'll need to be able to possibly identify an answer that has been simplified through the multiple choice. The other questions that are sort of more free response web work, they will accept the answers without simplification. Is that about right, Ryan?
That's exactly what I'd say. Yep, for the multiple choice ones, and it's similar to the old exams as well, that you have to be able to identify a simplified answer. However, yeah, in general, WebWorks pretty happy with any equivalent answers. I guess the only one counter example to this, which we will probably take the time in order to code this into WebWork as well, is that you can disable functions in WebWork. And similarly on exams, I've seen it marked down before, right? So if you leave your answer with the natural log of 1, right, in it, or something like this, I've seen it where people have been marked down for this, right? The natural log of 1 is of course equal to 0, and so you should make that simplification. So anything with natural logs or e's where they can actually be simplified, and I'd probably say the same goes for trig functions, right? So like sine of pi over 6, stuff like this. that those should be simplified. And I've seen people mark down for that. And in WebWork, we can just disable those functions. So you can say the answer is not allowed to have signs in it. So yeah. Any other questions? Or I guess we could even, if someone wants to speak, you could raise your hand and we could try that feature of these Zoom webinars as well.
So there's a question, will there be any checkbox question?
Will there be any checkbox question? So I'm assuming that this means like multiple select questions. Is that what you would guess, Alec?
Probably.
Yeah, I don't see why not, right? We definitely had examples where we had checkbox questions where there were multiple correct answers on quiz 5. And it seemed to work fairly well. Or I guess we recoded those because the partial credit on them doesn't work beautifully. And so we kind of broke it up into lots of pieces and we had students say true or false, right? And there was kind of drop down menus for those. Now I'm remembering, yeah. So the checkbox questions would probably be, instead we'll have true and false. So that way the partial credit's a little bit kinder, right? You get kind of more or less, if it's like a 5-point question, there's 5 checkboxes, then you would get 1 point for correctly identifying, should that box be checked true or should it be false, unchecked? And so that's the way we ended up coding quiz 5. So it's I think it worked well. So quiz 6 and the exam, I suspect are probably going to be coded similarly.
And let's see, a couple more questions here. First, just sort of, again, about the exam. Somebody's asking, will the exam have only multiple choice questions? No, it will also have your kind of typical WebWork questions where you're putting in, typing in answers. And to go along with that, somebody asks, are there WebWork questions where we will have to type a somewhat complicated answer into the text box? I don't want to lose points punching in a bunch of parentheses and such. We're trying to keep that, reasonable, but there will be ones where you have to put some answers in and there may be parentheses involved. We won't have any that are incredibly long, like the very longest ones you've seen in WebWork, but maybe somewhere sort of a little bit in the middle on that. And then for the questions about the problem that you just did, somebody asked, where did the -3/2 come from? And you want to take that, Ryan?
Yeah, so this really comes from the definition of these choose coefficients, right? These binomial coefficients as they're known. So in this -1/2 choose 2 means that you start at -1/2 and you drop by 1 each time. And then you multiply all these together and you have to know when to end, right? And you end after you multiply these 2 terms together. So right, this 2 down here signifies how far that you go before you stop. So the fact that we had 2 here, we went ahead and we multiplied 2 values together, starting at -1/2, dropping by 1 each time. And then we have the 2 factorial on the bottom, again, which comes from this 2 in the bottom down here. And so double check and make sure that you agree that this third, right, this -1/2 choose 3, then makes sense, right, with what I just told you. So we start at -1/2 and we drop by 1 each time. We multiply together a total of 3 values, right, because we're choosing 3. So that tells you when to stop. And then we divide by 3 factorial, which also comes from that 3. Okay, I think that's probably enough questions for now. We'll open it up certainly to more, but let's move on to example 2 here. Use series to evaluate this. And I love these types of problems personally. Maybe not everyone's, all of the instructors are quite on board as much as I am with these sorts of problems, but there are some very, these are actually impossible to integrate without series. That if you take this and you plug it into Wolfram Alpha or something like this, and I invite you to do this, that you just get basically a made up function. And it's because that there is no combination of other functions that we know and love. So sines, cosines, natural logs, any of these things that make this antiderivative. So the correct way to say this is that there's no elementary antiderivatives or no elementary closed form antiderivatives for this thing. So you have to use series in order to evaluate this out. And so if I had this question here on a quiz or an exam, right, we'd go down to the sheet of kind of all the power series that we know and love, right? That we have one for sine and we have one for cosine. I think even in the book there's one for tangent inverse. Of course, we have the 1 over 1 minus x, all of that sort of stuff, right? And you get all of these formulas. We have to decide which one does this look like, right? Which one should we actually use here? And the answer, maybe unsurprisingly, because we are in this section about the binomial theorem and everything, is that we're going to be using the binomial series. So the fact that we have the square root here, that's going to basically take this place of this k value, right? So the binomial series is great anytime you have any roots, square roots, cube roots, things like this, right? Because it goes 1 plus u to the kth power, and you're summing up, again, u to the n, from n equals 0 to infinity, and then you have these binomial coefficients in front of it. So it's going to be k choose n. And so we can, right, there's quite a bit of variation or variability here, right? You get to make a choice for u and you get to make a choice for k, and so it has nestled inside of it lots and lots of different power series. And so including this one. So let's go ahead and first we're going to try to recreate the square root of 1 plus x cubed. And so in that case, it's pretty fast. We can see we're going to choose u equaling x cubed, and this is going to be raised to the 1/2 power because that's the same thing as the square root. So again, u is going to be equal to x cubed, and k is going to be equal to 1/2. So if we go ahead and we plug these in, summing up from n equals 0 to infinity of, and now k again was 1/2. Choose n, and that's the thing that's going to vary. So first we'll plug in 0, and then 1, and then 2, and then 3, all so on and so forth. And then we have x cubed is our u, and we need to take u and raise it to the nth power. All right, so now we've recreated this function here, and next up we'd like to integrate it. And so this is yet another reason why I think it's a really good idea to go ahead and simplify, take one line to simplify first before we go and we integrate this thing. So with this choose, this binomial coefficient here, this 1/2 choose n, there's really no way to simplify that any better than what it already is. So we're going to leave this as is, but when you take powers and you raise it to more powers, remember they're multiplied together. So we get x to the 3 times n here. And this is really great because the next thing we're about to do is integrate, right? So if I went ahead and, oops, I was to fully rewrite this and say we're going to integrate both sides with respect to x, so dx, dx. That's what we're tasked with finding using power series. So the answer is, and now on the right-hand side here, remember you're allowed to distribute integrals across sums. So remember the sigma here is just adding a lot of things together. And so you can just integrate term by term. So you look at just each piece here. So I'm going to integrate each piece. And the other thing that you need to remember is that this right here doesn't have any x's in it. It's going to have lots of 1/2s and different numbers, n equals 0, n equals 1, n equals 2, but they're all going to be coefficients. They're all going to be constant with respect to x. And so you imagine, right, if this thing were to output, even though it probably never would, right, if it were to output, 2, or if it were to output 5 or something like this, right? Basically just these coefficients, whatever they happen to be, are along for the ride when you do the integral, right? So that's nice. And so the only bit that really has x's in it that you really have to worry about when you integrate with respect to x is this x to the 3nth power. So when you integrate, remember you need to raise your power by 1. So x raised to the 3n plus 1. And then you divide by that new exponent here. So that new exponent, that is 3n plus 1. And so my final answer, usually I like to rearrange these things. It depends on really what you're asked to do with it. Here, maybe you would argue that it's not so necessary, but I like to combine all of the coefficients together. So these are our like C sub n's sort of deal. Sometimes WebWork just asks for C sub n, so that would be one reason right there. And then I like to put all of our variables together. So of course, we only have the one there. It's x to the 3n plus 1. So this right here is the final answer, right? There's nothing more that I can do to simplify this anymore. This is the series evaluation. Of course, we could write it in the expanded form. This is in the sigma form, but it didn't say which way we had to do it. So I'm just going to leave it just as this. Of course, if we wanted to, we could expand it just by plugging in n equals 0, n equals 1, n equals 2, n equals 3, so on and so forth. And it's very possible, I know that you guys are, of course, interested in the quizzes and the exams and stuff like this. So, I mean, certainly we could give a box like this where you could plug in some values directly, in this sort of sigma notation, or we could just expand out maybe what this actually is and then make it multiple choice, which of the following, is equivalent to this essentially. Okay, I think that's probably a good time to maybe pause for some questions. What do you see, Alec?
One of them is asking, can we do the binomial series questions if it's something other than 1 plus x quantity to a power? Like, for example, if it was 2 plus x quantity to a power.
So yeah, that is a good question. So if we had something like 2 plus x to a power, let's just put it inside of a square root or something like this. This is actually, having some flashbacks, I guess, from chapter 6 and chapter 7. So what I would probably do here is that I would try to factor out a 2. So if I was to factor out a 2 from this, we'd have, and this is still within the square root, by the way. So something like this. And then I could distribute that square root to each piece. So I'd do the square root of 2 times the square root of 1 plus x over 2. And now you can see probably what your u value is going to be right here. And you could figure out what is the power series for this. And then once you have that power series, right, you just multiply it by root 2. And that would just be another part of your c sub n's, right? So you'd probably just have maybe like root 2 here as well. Yeah, so that's a fun question.
And then somebody asks, where did the 3n plus 1 come from in the problem you just did?
Yeah, you want to go ahead and take that one, Alec?
Sure. So I can't scroll your screen though.
All right, that's fair.
Scroll the screen.
Yeah, so it's kind of multiple steps in order to get why there's a 3n plus 1. So first of all, there's a 3n because we were very interested in this particular function, right? And that had 1 plus x cubed. So that's probably where the 3 comes from, right there. So we had our u value was this x cubed. And then remember, according to the binomial formula here, that this is going to be our u value raised to different powers. So x cubed raised to the nth power. And when you take powers and raise them to more powers, right, they multiply together. So that's where now the 3n first appears. And then we had to integrate this thing. So remember, if you wanted to integrate, for instance, just regular old x cubed, or if you wanted to integrate x to the 6th, remember what you do is that you add 1 to your power, and then you divide by that new power there. So likewise here, you would have x to the 7th and times 1/7. Remember, these are supposed to be antiderivatives, so if you take the derivative of these things, you should get back to where you started. So here we have a slightly more complicated thing though, right? 3n, but still the technique's the same. You add 1 to it, and then you divide by that new power. So if we add 1 to 3n, you get 3n plus 1, divide by that new power, there you go.
So in short, just power rule backward.
Yep, perfect. Okay, well, this kind of ends the binomial formula stuff. The rest of this section, I spend quite a bit of time going over these error formula stuff, right? Because I think that these are maybe some of the most complicated. They certainly have a lot of pieces to them. And so this, I got basically a couple more pages full of Taylor inequalities. What are kind of reasonable things to be done, for instance, even in time setting, right? So we'll do this here in class. And so, yeah, let's go through a couple of these. So in my 11.11a video, that's kind of where this version of Taylor inequality first appeared. I rewrote kind of what you saw in the book just a little bit, just to be very explicit, right? It uses like this absolute value of x minus a is less than or equal to d, which is fine, but I think that this is a little bit more clear. And then I kind of just wrote it out in words. So again, what we're trying to do with these Taylor inequalities and kind of the big story here is that you start off with a function. And one of the big uses for the Taylor polynomials, or the Taylor series, but then you just stop after a little while, is that they can approximate the function. And so when you make such an approximation, well, it may not be perfect, of course, but you have to wonder, well, how much are you going to be off by? And so this is the error, right? How far are you off by is called the error. And this is saying that we can actually bound the error, that we can figure out what's the worst case scenario. And it's given by this thing right here, which is still fairly complicated, right? And so it takes a bit to kind of dissect all of the pieces here and figure out what makes them all up. And in particular, I think the m is the most difficult. So m is supposed to be the maximum of that n plus first derivative on the interval that you're interested in. So that's the theory. And remember in 11.11, my first class video, I also had a link to the proof of this, right? Because anytime you see like a crazy formula like this, you have to wonder, where does this come from? Why does this work? And the answer is almost always in the proof, right? And so that's where you actually see why this is the formula to use and everything. But we want to focus on how can we actually use this to solve problems that would be reasonable, right, to show up on Weber-Comark quizzes, exams, things like that. So that's what I'd like to focus on a bit. And then we'd like to go through maybe all of the steps here. So here I have one that I like quite a bit. We start off with a function, and we want to calculate out t sub 2 of x. So remember, this is the second degree Taylor polynomial. That's where you first see this, t sub n of x. So it's the Taylor series, but you just stop after a certain point. So let's go ahead and calculate this out. The Taylor series for sine of x, I guess I knew this was a class question, so, but if it was a quiz or an exam, right, it may specify that we're centered at x equals 0. So let me just go ahead and write that in there. Centered at x equals 0. So there's a couple of ways that we could go about this. We could start taking derivatives of this thing, right? Derivatives of sine our function, and we know a way to calculate out Taylor polynomials using the derivative, and then we plug in our center value, in this case x equals 0, and we can actually get this. Another way to go, right, is that again we have this list, this great list of power series. And in particular, they were Maclaurin series that we got in 1110. And one of them that we have is for sine. So it goes that sine is equal to, or it converges, x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. And so remember, you have all of the odd powers. Sine is an odd function, right? Kind of this rotation, symmetry, and stuff. So all of the odd powers, it alternates back and forth, plus, minus, right? And you always divide by the factorial. And this would just go on forever. And so if you wanted to know what is the second degree Taylor polynomial, well, you would stop at degree 2. So this would be t sub 2 of x is going to be, and really if you wanted to be extra formal, right, all of these other degrees are there, they just have 0 coefficients. So you could really write this as 0 plus 1x plus 0x squared, and then that's where we stop, right? And then if we were to continue, right, if we wanted a third degree Taylor polynomial, we'd include that negative x cubed divided by 3 factorial. Right? So this right here is the second degree Taylor polynomial. Of course, it makes sense to simplify this down, and it's just regular old boring x. So there is the second degree Taylor polynomial centered at 0, aka a Maclaurin polynomial for sine. And so we would like to approximate sine of pi over 6 using this here. So using t sub 2, we'll approximate sine of pi over 6. So according to this, sine of pi over 6 is approximately equal to our second degree Taylor polynomial at pi over 6. So therefore, right, well, our second degree Taylor polynomial is quite boring. You just, everywhere you see your input, pi over 6 in this case, it's just that, it's just x. So it's just pi over 6. And I chose this value because it's nice. We can actually see here, right, sine of pi over 6 we know is 1/2. And so this is approximately equal to pi over 6. Remember, pi is just a little bit bigger than 3. So pi over 6 is close to 1/2. But of course, they're not equal, right? They're approximately the same, but they're not equal. And so the Taylor inequality can say how close these things actually are. How close is pi over 6 actually to 1/2? So that's the final bit, and that's using this box bit here, right? What is the maximum error in making this approximation? And so we need to go through and we need to identify kind of all of the pieces for this maximum error, right? There's, first of all, there's things like A that show up in the formula. There's N, there's D, oh, this complicated thing, right? This capital M, right? All of those combine in order to give us this maximum error. So let's start off with maybe some of the easy bets, right? So first of all, it's center, right? So we see this x minus a. Where is it centered about? Well, it's centered at x equals 0. So x equals 0 is the center. So that is our a value, our center value. It also specified to use the second degree Taylor polynomial. So that n value is going to be 2. Here's where it starts to get a little bit more complicated. We want to make sure, right, that we're choosing a good interval that this can actually speak about, right? And so we want to make sure that pi over 6 is in this interval. So remember, we have an interval centered about 0, and so our a value is 0. And we want to make sure that pi over 6 is actually in this interval. D right here is just quite literally the distance from the center. How far do you want to be able to move from the center and actually be able to speak about that interval? So in this case, we want to be able to move pi over 6 to the right, right? So we want to say something about this point over here. So we're going to choose our D value to be equal to pi over 6. And notice that we'll get everything in that case, 0 minus pi over 6, so that's going to be negative pi over 6, all the way up to 0 plus pi over 6, so that's going to be pi over 6. So our statement will actually be good for all of the values in here, that this approximation, this t sub 2 of x, right, just being x, so just swapping out, instead of sign, we're going to swap out x, whatever the input value is, will be, the error is maximized by this quantity actually on the entire interval here, not just at pi over 6. So that'll be quite nice. All right, so D is equal to this pi over 6. And lastly, the m value. So the m value, again, you should be thinking about maximum. So it's the maximum for the nth plus first derivative on this interval. So we just figured out we're on this interval from negative pi over 6 to pi over 6, right? Because we want to be able to speak about approximating sine of pi over 6 with this Taylor polynomial. So, okay, let's go ahead. That means we need to take some derivatives, right? N plus 1. So n in this case is 2, so we need to take 3 derivatives. So we start off with f of x is equal to sine. We need to calculate out the first derivative, the second derivative, and the n plus first derivative. So 2 plus 1 is the third derivative here. So let's go ahead, take some derivatives. Derivative of sine is cosine. Derivative of cosine is negative sine. Derivative of negative sine is negative cosine. And again, notice here, this one, actually the absolute values do come into play. And we're on this interval from negative pi over 6 to pi over 6. So let's go ahead and graph this really quick. Kind of in all of the previous videos and stuff, whenever I'm trying to find this maximum, you want to do a small sketch of the function if at all possible, unless there's a way to kind of easily say where the maximum is. So I'm going to go ahead and draw on the interval from negative pi over 6 to pi over 6, negative cosine. So if I was to do just regular old negative cosine, it would look something like this, right? So negative cosine would start at the valley here and start going up. And then of course it would cross and it would wiggle back and forth. If you were to do the absolute value of negative cosine, right, all of those values would now be positive. So this is going to actually look a lot like cosine. Remember, I'm just interested on this interval from negative pi over 6 to pi over 6. So this is where I would stop. After that, of course, it's going to go down, and then because it's the absolute value, it would actually go back up, stuff like this. But again, we're only interested on this interval from negative pi over 6 to pi over 6. So this right here is the absolute value of negative cosine of x. And like I mentioned, it looks a lot like regular old cosine for this particular piece. Okay, and we want to know what is the maximum, right? What is this m value that on this interval from negative pi over 6 to pi over 6, that cosine, as we found by taking all these derivatives, is maximized by, right? What is this m value? What is the maximum value? And so we can see based on this picture here that the maximum value actually lives right here in the middle. So right here in the middle, that's the maximum output. And again, remember this is negative cosine, the absolute value of that. And so this maximum value is going to be at height 1. So height 1, that right there is the maximum value. for the absolute value of negative cosine on this particular interval. And that makes a lot of sense, right? Negative cosine, sine, negative sine, all of this sort of stuff, right? They're bounded between -1 and 1 anyway. So that's kind of a safe bet for a lot of these sine and cosine sort of problems. So this right here, our m value is going to be 1. So now let's go ahead and combine it. Remember, the maximum error, or we can say error, is at most. And now we go and we grab all of these pieces, right? And we assemble them correctly. So we have m divided by n plus 1 factorial times this x minus a raised to the n plus first power. So let's go ahead and start assembling them down here. So m we found to be 1. N plus 1 factorial, so remember n was 2, so n plus 1 is going to be 3 factorial, times the absolute value of x minus a raised to the n plus first power. So n plus 1, 2 plus 1 is again 3. So this is fine and everything, right? But the error should be a number, right? And so we want to figure out maybe what is the worst case scenario for the error. And so I want to actually plug in a value for x, right? And so we want something that when cubed, and again, we're on this interval from -π/6 to π/6, -π/6 to π/6, that this gives the worst case scenario, right? Again, I just want a number here. So I'm going to plug in for x, and because we have these absolute values, can actually do either endpoint. And in these cases, it'll always be kind of either one of these endpoints is the correct answer. And because when you take the absolute value, either one is fine. So this is going to be π/6 minus 0 is of course π/6, and cube that. And so yeah, my final answer would be here pi cubed divided by 6 to the 4th power. This would be a perfectly fine answer to insert into WebWork, or to, right, if it was a multiple choice, it doesn't even look that bad, I suppose, but we could select something like this. All right, I've been speaking for a long time. I'm sure there are questions. Alec, what do we got?
First one here is, will we get docked or get a wrong answer if we use a d that is bigger than needed? And I'll say the short answer is yes. You can see from that interval there with that π/6 getting plugged in, but since you have control of the board there, Ryan, you might want to elaborate further.
No, yeah, I completely agree. You need to choose kind of the smallest d value possible, right? You want kind of the best of the worst case scenarios, right? And so if you choose a larger d value, it's kind of like saying that if the answer ended up being 10, right? And I said that the maximum error is 10. And someone else came around and said, well, I got out the answer of 100. I mean, 100 is technically true. I mean, it would be, you know, the error would be less than 100. But we can say something better about this, right? We can say that the error is definitely less than 10. And so, yeah, you want kind of the best of the worst case scenarios, I suppose, right? You actually want to figure out, you know, otherwise every answer could just be a trillion, right? Because the error is always going to be less than a trillion on all of these sorts of deals. So yeah, you do want to do as good a job possible bounding the error.
And then a similar question here from Jacob. How do you decide which is the worst to plug in here? Well, there's two different places where you're plugging things in, right? So you have to pay attention to the m, and that sort of maximum error where you're looking at that, see the green graph there, you're just picking literally the highest point on the graph, the maximum over that interval. And then there's another spot where you're deciding what to plug in for the x value in the interval, and that's going to come down to looking at the interval and taking the largest number in the interval. From -π/6 to π/6, the biggest value is π/6.
Yeah, this one's actually quite easy for the x values. It's always just one of the endpoints on your interval. So once you've identified your interval, just literally plug in either one of those, and they'll both give you out the correct answer because you're taking the absolute value here, and they'll give you the exact same answer. So this one's pretty straightforward. I mean, of course, you have to do it 5, 10 times, you know, really to get the hang of it. The more complicated one is this m value, right? You really do have to sketch the graph, or at least have a convincing reason of where the maximum should be, even if the graph is maybe too complicated to sketch. In this case, it was pretty easy to sketch, so we just did that. But otherwise, you have to kind of reason out where should this maximum m value be.
Just to elaborate on that, for example, if you knew, for example, that you had a function that was definitely increasing, then you could use the right endpoint, find that function value, and that's where you're going to have your largest value. If you knew something was decreasing, you could take the left endpoint and you know that the function value there would be the largest in the interval.
Yeah, and then we actually have a problem like this, actually example 20, I believe, for this one, or if I forget if the enumeration's the same. Nope, the numbering is different here. But this one right here, you'll see you'll take some derivatives, and actually it's too complicated to sketch. So you need to look at kind of what makes up the derivative, and you'll have a good reason to believe that it's an increasing function. And yeah, exactly like you said, Alec, you'll be able to say where the maximum is.
Right, and there a similar question here. The last two that came in that were very similar to both of those. So if the endpoints were different numbers, you would choose the one with a higher value output. And yes, that's correct. So, and that also goes along with if the center somewhere other than 0, would only one endpoint work? Yes, one of them would be the one that would give you the maximum.
Yeah, and we'll see with actually. So we have. Example 4 here will answer that question as well. And so that'll be something good that we can bring up. This is centered around 1, and you can see that we have 0.9 and 1.1. And so when we get to that, I'll make sure to highlight that as well.
Yep, I think most of the other questions here are going to be answered by that example. So.
Okay, wonderful. So let's go ahead and continue. Using Taylor inequality, find the maximum error in approximating f of x is equal to the square root of x with its second degree Taylor polynomial centered at a equals 1. So maximum error, so yes, Taylor inequality. So these are some of the highlight words here. Anytime you see maximum error, or in this case, it just said Taylor inequality, right? That's the real indicator to use Taylor inequality. We have a function. We want to approximate that function with its second degree Taylor polynomial. So already we're seeing here that n should be equal to 2, according to these words here. It's just very explicit about the a value. So a is equal to 1. And then we can also get the distance, right? This d value. So remember our center here. And we want to go to a plus d and a minus d, right? So if we're centered here at 1, and we want to be able to make it to 1.1 and 0.9, that means we want to be able to take a step of 0.1 off of our center, right? So in this case, our distance is going to be 0.1. And of course, we can see that, 1 plus 0.1, that gives us the 1.1, of course. And if we do 1 minus 0.1, that gives us the 0.9. All right, so we have n, we have a, we have our d value. So we're having quite a bit here. I guess, on this list of things that we need, probably next up would be m, right? We've done quite a bit. We just need to know what this m value is. And so for m, this is the one where you have to take lots of derivatives, right? And then we have to argue a little bit about what is the maximum value. So, okay, we need to take 3 derivatives, right? N plus first derivative, so n was 2, so we need to take 3 derivatives. Starting off, our original function is just x to the 1/2. If we take 1 derivative, that 1/2 is going to come down, reducing our power by 1 here. Taking a second derivative, we're going to have -1/4 x to the -3/2. So now this -1/2 came down. -1/2 times 1/2 gave us the -1/4, and we reduced our power 1 more time. And finally, for our third derivative here, bring the power down yet again. So we're going to have +3/8, reduce our power by 1. So we have x to the -5/2. And there we go. We now have 3 derivatives, right? And so we need to think about this, our third derivative here. We need to know where is the maximum value, right? Where's the maximum value? And we're very interested on this interval. The interval that we're interested in is from 0.9 to 1.1. And so at this point, I've said this quite a lot in my class anyway, right? When you're taking derivatives, I think having these, kind of the function in this form where you have the negative exponents and everything is quite good, because the derivatives come very quickly because of the power rule. But when you actually take a step back and you're doing something besides calculus, right? If you're trying to do some algebra or see what this actually looks like, I think these negative exponents are actually quite deceptive. And so I would like to go ahead and rewrite this. Remember, anytime you have a negative exponent, it's actually secret division, right? So this thing's actually in the denominator. And so let's actually view this for what it really is here. I'm going to go ahead and put this down into the denominator. And so I have 3 over 8 times x to the 5/2 power. And I need to think about, and this is, again, this is actually an example of one where maybe I don't want to sketch the graph of this. I mean, you could kind of argue about what it would be, and you'd probably be correct. And of course, you know, we do have a bit of time. I mean, we could go on Desmos or something like this and actually look at what it is. But let's just try to figure out, you know, logically where the maximum should be. And the thing is here is that our inputs, our x values, are in the denominator. And so again, if you were to plug in kind of, oops, I forgot my right parenthesis up here. If you were to plug in larger values into the denominator, right, you're dividing by more, you get a smaller output. So again, kind of when you divide by a bigger thing, and the classic example that I like to use, you know, 1/2 versus 1/3, it's overly simplified, but it's the right idea, right? When you divide by a bigger number, 3, you get out a smaller output overall. Versus, right, when you divide by 1/2, a smaller number, right, you get a bigger thing. And so if you wanted to know what the maximum of this was, well, you'd want to divide by the smallest thing possible. And on this interval, the smallest thing possible is happening here at 0.9. So the maximum value is going to happen when you plug in 0.9 in everywhere you see an x. So this is personally how I would argue this. You could also say something about how it's just like the reciprocal function being scaled. So I mean, if you were trying to draw a picture of it, you would get something that looks like this. So on the interval from 0.9 to 1.1, you do see that this is a decreasing function. And so you'll see that your maximum is actually over here on the left-hand side. The same for any decreasing function. So that's another way that you could go about it, but this one doesn't require any graphing whatsoever. Okay, so that is our m value, the most complicated bit. Now let's go ahead and assemble all of the pieces. So when I assemble all of the pieces, remember I start off with m, so 3/8, I also need this 0.9 raised to the 5/2 power, so that's m, divided by n plus 1 factorial. So again, n was 2, so plus 1 is going to be 3 factorial. And then we multiply by the absolute value of x minus a raised to the n plus first power. So the n plus first power, again, 2 plus 1 is 3, and our error is less than or equal to this here. And of course, so we could simplify a little bit, right? This 3 factorial and this 3 will cancel out. We have fractions over fractions. So let's go ahead and clean this up a little bit here. So I'm going to have 1 divided by, and remember 3 factorial is the same thing as 6. So 3 by 6, this is going to be 1/2. And we also have an 8 down here. So I'm going to write 1/16. And then we have this nasty bit, this 0.9 raised to the 5/2 power. And then here's where we got to that great question about you know, these endpoints and this different center here. So again, remember, we're on this interval from 0.9 to 1.1. And so we could ask, well, what happens if I plug in either one of these endpoints? So if I plug in 1.1, for instance, well, I need to subtract 1 from it. So I'm going to have the absolute value of 0.1 being cubed. Versus, right, if you were to plug in 0.9, so if you were to plug in 0.9 and subtract 1 away from it, notice this is going to give you negative 0.1. And cube that. But remember, it's inside of these absolute values. So actually, when you apply the absolute values, either way, you get the same result. So either way, you get the same result. And that's just, again, because we have our interval that's centered about, well, the center, right? So it's centered about 1. And it's taking a distance of 0.1 off, either to the left or to the right. So yes, either, in this case, either one of these ends up yielding the same result. And so yeah, my final answer here, well, of course I could leave it just as this. I'd probably get rid of the absolute values. But you know, 0.1 is the same thing as 1/10. So 1/10 times 1/10 times 1/10 is going to be 1/1000th. You could combine the 1/1000th and the 16, and right, you could do a few other small things. But yes, this is going to be probably as simplified as we can get it, really. Any questions here?
There was a question about back on the previous one. It said if you weren't given the pi over 6, how would you determine the interval? And then went on to kind of follow up and said, for example, web work 10 does not give a value to estimate and says to calculate the maximum error.
Yeah, so if you weren't given a pi over 6, I suppose you could leave it with just the x in here. And I have seen a remainder theorem. I forget, maybe it's in 11.10 of our book, or maybe it's another calculus book that I'm confusing it with. But I have seen these where you have the error depend on x. So you have this, sometimes it's denoted with r sub n of x. So rather than getting a number out, you could say, for in this case, right, we were dealing with second degree stuff, right? We could say the remainder, which is again just another kind of fancy term for error, right? So the remainder or the error for the second degree Taylor polynomial, but then leaving it in terms of x. So that way you can plug in an x value later, essentially, if you wanted to. It's like the derivative, right? First, we started off taking derivatives at particular points and talking about slopes of tangent lines, and then we built this derivative function. And so it's the same thing here, where now you're kind of building a remainder function. And so you could just leave the x's there, but then you would need some kind of global maximum for your n plus first derivative. So it will only work in a handful of cases. It would work for sine and cosine, right? Because it does have a global maximum, right? Sine and cosine are they never get out of this 1, right? M equals 1 would always be a standard maximum for sine and cosine. So it would work for a handful of functions, but otherwise you need to work on what is the m value.
And just to follow up a teeny bit on the web work number 10, I just pulled it up to look at it. That's actually the one where you're given the decimals graph.
Oh, okay.
So on that one, you're just really looking for the maximum distance between those two functions.
Oh, okay. Yep. That makes sense then.
So just kind of look out on either end and see where you see kind of the biggest gap between the actual function and the Taylor approximation for the function. And that's what you'd use.
All right. Any other questions?
That's it that I see right now.
Okay. Let's go ahead. I have one more page here. I have this example, which again, kind of using a second degree Maclaurin polynomial. So it's very good, specifying what the center is on a specified interval. And then I also have this one. This one just quite literally is from a previous exam, so maybe as you're reviewing, you'll come across this naturally anyway. But I see that we have another 3 minutes left, so maybe I won't feel so bad skipping this one. If you would like to work on it on your own and verify the answer, I can tell you that the correct answer is A. So you can verify this, and I'd be happy to answer questions regarding this problem on Piazza or maybe in our next class or something like this. But let's go ahead and spend a little bit of time working on this one. So again, same sort of setup, but now we have a different function. So again, maximum error, it does specify Taylor inequality, but maybe for this one, pretend that it doesn't even say this, right? It just says find the maximum error, right? And the main tool that we have for finding error is the Taylor inequality. We have a function, it's specified its second degree Maclaurin polynomial. So remember, a Maclaurin polynomial is just a Taylor polynomial that's centered at 0. So Maclaurin here is saying that A is going to be equal to 0. Because it's the second degree polynomial, right, it's going to be n is equal to 2. And similar to maybe the first problem we did, we can find our d value. Because we want to say something about what's happening from negative pi over 6 to pi over 6, right, the maximum distance that we take away from our center is going to be pi over 6. We do this to the right and we do it to the left. So in this case, our d is going to be pi over 6. But again, kind of this is really explicit here. This is just, it's already stating what our interval is. So really, we don't need much more than that. Okay, so we have all of these kind of smaller pieces, the nicer pieces. The most complicated one is, of course, the m value. So this is where we need to take quite a few derivatives in order to come up with this. So let's go ahead and take some derivatives. First derivative, second derivative, and because we're using the second degree, remember we need n plus 1 derivatives. So we need 3 derivatives. When I take the derivative of secant, I get secant tangent. When I take the derivative of secant tangent, well, sadly, I need to use the product rule, right? There's nothing fast about this, so we'll just take a little bit of time. Product rule goes the derivative of the first, so the derivative of secant is secant tangent, times the second, plus the first, times the derivative of the second, and the derivative of tangent is secant squared. So actually, let me go ahead and take a line to clean this up a little bit. Secant x times tangent squared x plus secant cubed x. And finally, as you can probably guess, the third derivative is going to be a little bit messy here. So again, this bit, we're going to need the product rule. So the derivative of the first, derivative of secant is secant tangent, times the second. Second is tangent squared. So let me just go ahead and simplify that and write this as tangent cubed here. Plus the first times the derivative of the second. And now we have a chain rule going on, right? Because this is tangent squared. So the 2 comes down, reduce our power by 1. So it's tangent to the first power. Then we multiply by the derivative of the inside. And the derivative of tangent is secant squared. And of course, we could go ahead. We already have some secants back here, so they could all multiply together, and this is going to have a secant cubed once we've simplified it all down. Okay, and then plus, can't forget, there's an extra piece, this secant cubed. So take the derivative of secant cubed or something cubed, the 3 comes down, reduce your power by 1, then multiply by the derivative of the inside. And the derivative of secant is secant tangent. Again, there's already a couple secants there, so we could combine. We have a total of 3 secants. So let's just put this as secant cubed. So we have something like that. Notice that here we have 3 secant cubed tangent x, and then here we have 2 of them, right? So 2 secant cubed tangent x. So this is going to be secant x tangent cubed x, and there's 5 of these things altogether. And the last bit, and maybe this is optional, we could leave it just like this, but again, we're trying to figure out what the maximum is. And so it really helps to be able to think about what secant and tangent actually look like. So I'm going to leave it just as this, and we're going to think just about, because right, if I had to sketch a graph of this, it would be a nightmare. But we can actually say just because of what it's made up of, where the maximum is going to be. And it's made up of secants and tangents. And so if I was to draw a small picture of secant, for instance, secant, again, the reciprocal of cosine, it looks something like this. So it has these like cups here, and then it goes off to infinity at its asymptotes, which are at pi over 2 and negative pi over 2. And then it kind of flips and does a bunch of stuff. But again, we're just on this interval from pi over 6, negative pi over 6 to pi over 6. So we can see that the maximum is actually kind of farther away, right? Those are pi over 2. So we're kind of at the pi over 6's, negative pi over 6 or positive pi over 6. That's where the maximum is going to be. For tangent, if I was to draw a small picture of tangent, tangent has, again, asymptotes. It goes off to infinity at, kind of a coincidence here, negative pi over 2 and pi over 2. Again, we're only interested on a particular interval, right, from negative pi over 6 to pi over 6. And if you want the maximum, well, the maximum's over here, right? So at pi over 6. And notice that's also, there's a maximum for secant. So at pi over 6, it maximizes both secant and tangent. So it maximizes everything, right? And so when you multiply all these together, right, this is where the maximum value is going to live, at x equals pi over 6. So this is a fairly complicated one. I'm not sure if this would be completely appropriate, right? Usually when I bring up something like this, students will inevitably ask, right, is something like this reasonable for a quiz or an exam? This one's, a tough one, right? This would certainly be maybe on the challenging page or something like this, which for our exams, I've not heard anyone bring up formally any challenging questions or challenging page. I'm sure that there will be questions that are more difficult than others. But as of right now, I don't really know. I guess, Alec, have you heard anything about a challenging page or challenging problem as far as exam 2 goes?
I have not.
Okay. So that's what we know, is that no one's been talking about bringing up a challenging problem. Of course, there will be some that are more conceptual. right? Just because it is open note and all this sort of stuff. And so certainly there could be some more conceptual questions, but nothing that we're formally calling, a challenging page or anything like this.
I think that's right. Jacob's just chiming in saying, please no challenge problems. And I think that's the way we're leaning to, Jacob.
Yep.
And let's see, a couple quick questions here. You've got one that says, did you miss the secant cubed in the third derivative?
Maybe at one point where I hadn't gotten to it yet, but we did come back around and we did get the secant
came back around to it. Yep. Okay. That's what I thought. I just couldn't scroll up to see that for sure. Another one says, I have a question about the homework. It says that the parametric curves are due on 4/6. Will this be moved, et cetera? Let me just give you a tiny bit of background on that. This is to make your guys' lives easier. The exam is sort of set for when it's set by the university and having the math exam spread out. So we have to have the exam in the week that we have the exam. We used to have sections 10.1 and 10.3 on exam 2, and we just thought it was kind of a lot for you guys to try and learn all of that and retain all of it. We thought it was just a lot friendlier to just have chapter 11. The only downside is you do have to move forward, and we still need to keep learning stuff, or else it would all be crammed together after the exam and it would be going way too fast. So yeah, unfortunately, you do have to learn 10.1 before the exam. You do have web work on it due before the exam, but you don't have to worry about it being on the exam. That stuff will just be on the final. And that's hopefully to make your life easier, not harder.
And while you were talking, I decided to continue just because it would be nice to finish up this problem and see what the actual answer is before we end here. So I went ahead and we said that the maximum was at pi over 6. Of course, in order to plug this into our third derivative, that takes a little bit. It's nice to take a quick pit stop and just say what tangent of pi over 6 and secant of pi over 6 is. So just using our unit circles for those, for the tangent. And remember, this looks a lot like root 3 over 2, but of course it's the reciprocal of that, right? Because secant is the reciprocal of cosine. So instead of root 3 over 2, it's 2 over root 3. And when you plug all these things in, and I just skipped steps because I see we're already over, so I want to be as respectful as possible of people's time. Verify for me, and please tell me if I'm wrong, but when I did this earlier, I got 14/3. So that is our m value, right? When you plug in pi over 6 into our third derivative, that's the maximum the third derivative can be on this interval. And so I went ahead and I plugged in our m, our n plus 1 factorial, so 3 factorial. And again, we're multiplying by this absolute value of x minus 0. Again, we're on this interval from negative pi over 6 to pi over 6. And therefore, if you plug in kind of either one of these endpoints, and I guess I could even simplify this, 6 times 3 is going to be 18. You could simplify even more, but you're going to get pi over 6. Absolute value of that is, well, it's already positive. Cube that, there you go. So this right here would be the final answer. And like I said, this is kind of the upper end of the spectrum as far as what's reasonable in a time setting. And even this, like, it took a lot of pieces in order to put it all together. Okay. Last questions. So yeah, if you have any last questions, throw them in there. We'll stick around for, maybe another 5 minutes or so, and we'll just, I'm sure there's a lot of administrative questions and things like this. We'd be happy to answer them now. And then, yeah, thanks for joining, by the way. If any of you have to leave, I see that there's people signing off and stuff like this. And so, yeah, we will post this as soon as possible. It takes some time to render and stuff, so we'll post this on YouTube. But yeah, we'll stick around for some questions. So what can we answer for you? See anything interesting out there, Alec?
Not really. An anonymous attendee says, are you guys keeping the problem page a secret? I would say no, it's just we're not in the absolute final form of the exam yet, but I think we could probably say that we're probably not going to have a challenge page, and maybe firm that up for sure in an email or announcement later.
Yeah, this is something that really, the course supervisor usually, we have a draft exam, I guess is a good starting point to say. And as of right now, there's nothing on the draft exam that says challenging page. But, it's good to have everyone on board, and especially the course supervisor, before I come out and formally say it's definitely one way or another. And so, yeah, that's the only, it's not a secret. It's just, I don't know what the answer is.
Right. Jacob asks, will answers for the rest of this worksheet be posted online?
Yes. So I
Kind
mean,
of just did it
certainly
right
you
there, right?
you see this, and there's the rest of the worksheet. I think this went rather well. Of course, I'll see what the rest of the process looks like as far as rendering the video, uploading it to YouTube, and stuff like this. But yeah, one thing that Alec and myself were talking about were, doing more of these sort of sessions, including 10.1 and 10.3, maybe on Wednesday and Friday, assuming that, yeah, nothing went too terribly wrong here. So right now I'm calling this a tentative success. And so, yeah, I plan on doing the rest of the problems on this worksheet, hopefully in a live session like this. Worst case scenario would be I'll just do them on my own and upload them to YouTube later.
And let's see, 2 more questions here. When is tomorrow's lab due?
So the lab, I believe you have all day Tuesday and Wednesday to do it. But this is a fine thing. Why don't we click on this? That shouldn't be confused with the pre-lab. The pre-lab you have today and tomorrow, and it's open until 11:59 Eastern Standard Time, sort of deal. And then, so yeah, so complete the pre-lab assignment here, and that's open on Monday and Tuesday. And so again, we kind of revolve around Eastern Standard Time. Ooh, looks like I need to update payment details on, okay, that's fine. But yeah, so Monday or Tuesday, so it is open now, you could do it. The lab, it's open all day Tuesday and Wednesday. So same sort of deal. You don't have to worry about your recitation time or anything like that anymore. But just by 11:59 Eastern Standard Time, you should have lab 6 put up by Wednesday.
Good. And somebody asked, if these lectures carry on in the future, will it be the same time, or will they be will be at the same time, 2 o'clock?
Yeah, it's I think 2 o'clock works fairly well, especially I know the majority of the students are in the continental US, and so this way, even folks in California and stuff, we're not making anyone wake up at 6 a.m., for instance, to do this. So I'm relatively happy with the 2 p.m. time slot.
I agree. Yep. And then also, I really enjoyed this live lecture format. Not a question, just more live sessions. Sounds like people are liking it. I thought it was pretty good too.
All right, excellent. Well, I think this is where we'll end it. Thank you so much, everyone, for attending. We really appreciate it. And yeah, I also enjoyed it. And so hopefully we'll see you back here on Wednesday. Again, I'll make this formal once I actually go through the whole process of rendering the video, uploading it and everything. And hopefully the file size isn't too monstrously large. But yeah, I'm cautiously optimistic. Wednesday we'll be back. All right. Thanks again, guys. Bye.
Take care, everybody.